All right, we are looking at oscillation questions. Our first problem set, 7.1. We're going to look at number 1, number 8, and number 10. So number 1, a 1 kilogram block is attached to a spring with a spring constant 16 newtons per meter. While the block is sitting at rest, a student hits it with a hammer and almost instantaneously gives it a speed of 40 centimeters per second. All right, so let's just parse that. All right, it's attached to a spring, so we're not told about its orientation. Let's guess that it's horizontal. And it's attached to a spring like this. So if we're told that it's initially at rest, then it's at equilibrium. It's just sitting there. So let's call that location position 0. And then gets hit with a hammer, it's given a speed of 40 centimeters per second. So let's say the hammer comes in like this, gives it a good whack, and instantly it's moving with some velocity in that direction. So its velocity, I'm going to call this at point 1, is 0.4 meters per second. And we need to know a few things about this. So right off the bat, we can say that its position at its energy at position 0 is exclusively kinetic because the spring is not compressed or stretched. So we've got, sort of in the general form of the conservation of energy would say that the kinetic energy at a location plus its potential energy at that location is going to be equal to the sum of those two at any other location. So one thing we're interested in is the amplitude of the oscillation. So let's call position 2 to be the location where it comes to rest, x equals a, where it comes to rest, where all of its kinetic energy turns into spring potential energy, and at that point it is going to stop, so it's going to turn around, and so the maximum displacement that it undergoes is what we're going to call the amplitude of its oscillation. So we're going to call that location 2. So the kinetic energy plus potential energy at location 2. Well, its potential energy at location 1 is 0, and its kinetic energy at location 2 is 0, because we're choosing our locations thoughtfully. So we got 1/2 mv squared equals 1/2 kx squared. This canceling of 1/2 is going to happen all the time in these kinds of problems. And we've got the mass, we've got its velocity, and we've got the spring constant. So all that's left to find is this x, or in this case, I'm going to replace that with a because we're looking for the amplitude. In this case, the x displacement will be the maximum displacement. So mass is 1 times the velocity, which is 0.4 squared equals 16 times a squared. And when we do the math, which I've cooked earlier, we find out that the amplitude is 0.1 meters. All right, so what's the block's speed at the point where the displacement is half of the amplitude? All right, so that's some spot in between here, which I'm going to draw in red. So at that point, I'm going to call that location 3. At that point, the spring is partly compressed, but the block is still moving. So whatever the total energy is, though it remains constant, at that moment, it is going to be both kinetic and spring potential energy. So I'm going to start with the kinetic energy at point 1, which we know, we have all that information, and that's going to be equal to the kinetic energy at point 3 plus the spring potential energy at point 3. So we got 1/2 mv squared at point 1 is going to equal 1/2 mv squared at point 3 plus 1/2 kx squared, and that's its location at point 3. So the location at point 3 is going to be half of the amplitude, so that is going to be 0.05 meters. All right, cancel out all the halves. we got mass is 1, so we got 1 times 0.4 squared equals, again, 1 times velocity 3 squared, that's what we're interested in, plus k, which is 16, times x, which is 0.05 squared. And so we got 0.16 equals v3 squared plus 0.04. It turns out that v3 is 0.35 meters per second. Yeah, I skipped a little bit of algebra, but I think you can do that. So that's what's going on with problem number 1. Problem number 8. We've got a large block of mass, 24 kilograms, with an 8 kilogram block sitting atop, executing simple horizontal simple harmonic motion as it slides across a frictionless surface with some frequency. So like a little wall here, a floor, a spring, and this contraption is oscillating left and right. So we've got a frequency is 0.97 hertz. We've got a total mass of 32 kilograms. And we know something about the friction. The coefficient of static friction between the two, that's in between there, is 0.41. So what maximum amplitude of oscillation can the system have if the block is not to slip? So considering we're talking about not slipping and we're talking about friction, we're talking about forces, and with forces comes acceleration. So we can look at the acceleration formula for oscillations. Acceleration is omega squared times x, or particularly the maximum acceleration is omega squared times the amplitude. And so we're interested in the maximum amplitude. So we're interested in solving for A. But in order to get there, we need, all these other things. We need omega, and we need the acceleration. So let's figure out omega first. Omega, what is the angular frequency? How quickly is it accomplishing these oscillations? Angular frequency is, there's a couple formulas for that. It's either 2 pi over period or 2 pi times the frequency. Well, we got the frequency, so let's use that. So that's going to be, plug those values in, and it's going to be 6.09 radians per second. Put a little squiggle around that. Now, the maximum acceleration. Well, let's think about forces. The only force acting on the 8 kilogram block horizontally is going to be friction. And friction equals mu times the normal force. Now, there's no exotic forces on this vertically. It's just the normal force up and mg down. So it works out that friction is going to be equal to mu mg. And that force is responsible for accelerating the 8 kilogram block. All right, well, it's an 8 kilogram block, both sides, so the m's cancel out. So we get mu times g equals the acceleration. The maximum acceleration that this thing can withstand can't exceed the frictional force. Can't exceed the force that friction could provide, or can't exceed the acceleration that the friction could provide. So mu is 0.41 times g, which is 10, gives us a maximum acceleration of 4.1 meters per second squared. All right, so we know how quickly this thing is making itself go back and forth, and we know what its maximum acceleration could be, and let's plug those in. 4.1 equals omega 6.09 squared times the maximum amplitude. And you crunch the numbers and you find out that the maximum amplitude is 0.11 meters. And lastly, number 10, a block of unknown mass. This is where it gets tricky because pretty much, all of our kinetic energy equations and the period for the springs, 2 pi root m over k, mass is in most of this stuff. When a spring is pushing and pulling on a mass, it certainly depends on how big the mass is. That will influence the behavior of how it oscillates. So without knowing the mass, we may be in for a little bit more of a mathematical challenge. It's attached to a spring of constant 5.5 newtons per meter. It undergoes simple harmonic motion with an amplitude of 0.074 meters when the mass is halfway between its equilibrium position and the endpoint. All right, so at x equals half of the amplitude, its speed at that point, I'm going to call this x half and v half, its speed at that point is 0.278 meters per second. Calculate the mass of the block. All right. Well, we're told something about its position, told something about its velocity, and that strongly suggests to me that we should consider its energy. We know something about its kinetic energy, and we know something about its potential energy. Question is, we don't know what its total energy is, but at least we know what its maximum amplitude is. So I'm going to call this kinetic energy at the half location plus its potential energy at the half location is going to be equal to total energy, which would be its full energy, spring energy at its maximum amplitude. So at the very least, we can sort of start creating an expression. And this is your general problem-solving strategy. If you don't immediately know how to solve it, start building an equation somewhere. Start somewhere. Start with what you have and build up from there. Maybe as you go, things will start to visually come together. You'll start to recognize, oh, this can go into there. If you don't know what to do, start somewhere. And so I'm going to start with conservation of energy. So 1/2 mv squared plus 1/2 kx squared equals 1/2 ka squared. Get rid of all the halves. The mass is what we don't know. And so we've got mass times its half velocity, its velocity at the halfway point, which is 0.278 squared, plus spring constant k, 5.5 times x, that's the half x, which is going to be half of the amplitude. So it's going to be 0.074 over 2 squared equals the spring constant 5.5 times the full amplitude squared, which is 0.074 squared. Oh, this is actually not terrible. We've got everything we need except the mass. All right, so 0.278 squared is, we got mass times 0.0773, I'll just carry a bunch of decimal places, plus 0.074 divided by 2, square that, times 5.5, that's 0.0075 equals 0.074 squared times 5.5 is 0.03018, 0.03. All right, so 0.03 minus 0.0075 So we got 0.0773 m equals 0.0226. So the mass equals 0.29 kilograms. Bingo.